When you do Euler's method, listen to this sweet ballad. We will teach you how to approximate given initial value differential equation 2. Take step size into account and plug it in. Initial value is f of a. Plug initial x for a into b. Differential this f prime of a you get is plugged in now, don't you fret. X minus a is simply the step size. Multiply f prime of a step size, then add it all to f of a to get to the value that they ask for using a number of steps. Repeat using x and y from the step before. X will be seen as a and y will be called of f of a. Keep the step size when you do Euler's method. Listen to this sweet ballad. It all makes sense now, doesn't it? It's not that bad.
Example 1 states use Euler's method with a step size of 0.1 to estimate y of 0.2, where y of x is the solution of the initial value problem y prime equals y plus xy, y of 0 equals 1. First, we start off with the equation for all Euler's method problems. Y of x equals y of a plus y prime of a times x minus a, where x minus a is the step size. Since we're approximating with a step size of 0.1, our first x value is x equals 0.1 and a equals 0. Since x minus a is the step size, we plug in 0.1 for that. Since we were not given y prime of 0, we must plug in the initial value into the given derivative equation, which results in y prime of 0 equals 1. Now we can plug in the derivative into the Euler's method equation. Y of 0.1 equals 1 plus 1 times 0.1, which equals 1.1. Now we can use this value for the initial condition for y of 0.2. Y of 0.2 equals y of 0.1 plus y prime of 0.1 times 0.1, which is the step size. Since we don't know y prime of 0.1, we can plug in the values of the points that we just found into the given derivative equation. This results in y prime of 0.1 equal 1.1 plus 0.1 times 1.1. Y prime of 0.1 equals 1.21. Now we can plug in y prime of 0.1 into the Euler's method equation. Y of 0.2 equals 1.1 plus 1.21 times 0.1, which is the step size. We do the algebra and find out that y of 0.2 equals 1.221. This is what results from using Euler's method with a step size of 0.1. But remember, this is only an approximation, and the only way to find the exact answer would be to plug it into your calculator. The answer to the question is 0.2, 1.221. In part B of question 1, we're asked to graph the direction field for the given differential equation y prime equals y plus xy. When we plug in different x and y values into the given differential equation, we get this direction field. A chart of the numbers we plugged in is shown here.
I plugged in different x and y values to the derivative equation. If the resulting number is a higher positive number, it indicates a high positive slope. If the resulting number is a low negative number, that indicates a steep decreasing negative slope. Oh no, our company's debt is rising.
Chillax, man. We can figure out how much it will rise over the next few months if we know our current spending.
But I don't know our current spending. Our monthly report hasn't come out yet.
Well, alright. Do you know the rate at which we've been spending our money?
Well, I know the function for the rate at which we've been spending the money.
Great. Then we can just use direction fields to see at least the general trend for all the possible current spending values.
Perfect. Okay, let's start. Oh wait, the monthly report just came out. We've spent $50,000 this month.
Okay, great. Now we can just figure out how much we'll be spending even in the next 10 years by using Euler's method and the direction field we already made.
Perfect.